Our speaker is elmongi. He's a PhD student at computer science in University KU Leuven, and he will tell us how to use Julia to build a quantum state solver.
Thank you. Good afternoon, everyone. I'm working on the quantized system solver.jl, which is a package developed as a solver for another tool that is being developed in the Belgian Royal Military Academy. So to do that, I'll start by an introduction, then I'll explain what this QSS solver is and why should we use it, and then talk a little bit about the software and the improvements of this method. So introduction is, let's say that you came up with a great idea that you want to test in one of these complicated systems. Then obviously you cannot test it directly because it can be costly in terms of time and money, as well as dangerous. So we all know that simulation is the answer to this problem. But there is already many tools out there. But there is the need always to invent a new tool depending on the special needs. So is that? So, as I said, in the Royal Military Academy, there is a tool called JIFSO. It's a Julia Interoperable Framework for Simulation and Optimization. And there is the need to have a solver that works underneath this tool. And that solver is the QSS solver. So QSS is basically a set of explicit and implicit methods that solve differential equations with events. So the special thing is the events. So to compare it to the classical integration methods, the QSS at a step will update only one variable, while, as we know, in the classic methods, at each step all variables get updated. And there is a new variable that shadows this variable x, and we call that variable q. So that's the added thing for this QSS method, is this q value, which is depending on the method explicit, then will be the old value of x. If we are using the implicit method of QSS, then q will be the future value of x. To explain it a little bit more, I have this example. Let's say we have a system of two differential equations. Step one, for the classic methods, both variables x1 and x2 will get updated. For the QSS, let's say only variable 1 needs an update because variable 2 is slow and we don't need to update it. So for the explicit, we know we have q is the old value of x. So at this point, we have set q as the old value of x, while in the implicit, we set q as a future value of x. So the algorithm, in simple words, will look for what variable needs an update, and then we'll update that variable. Do I have a pointer, or does this work as a pointer? Okay. So, and then I update this variable and update its quantized variable, and then see if other variables depend on this variable, and I only update those, and see if there are any events that depend on this variable xi, and then I check if those events need or the zero crossing for those events need to be checked. So besides this variable q, I also have a set of dependencies matrices that are built up front that I will use to check which variables need an update. Then, besides the QSS from the beginning, we see that it has cheaper steps. Also, the implicit method has a huge advantage. So we know that in the classic methods, if we have an implicit algorithm, then we have this unknown x, which is a vector, since we need to update all the variables. And if we want to look or find this x, then the math will lead us to a matrix inversion in the size of the system. While in QSS, since we don't need to update all variables at the same time, so x is just a scalar. And then the same equation will lead us to just a normal expression. So that's a huge advantage in the implicit case. Just to note or to mention that sometimes in QSS we need to update two variables at the same time. And in that case, we have a 2x2 matrix, so it's not costly in that case. So that's a huge advantage for QSS. The next advantage is the discontinuity. So if we have a discontinuity right here in the classic methods, at each step, we'll check is this function crossed 0 or not. While for QSS, since we have the dependency matrix, so if let's say variable xk changed, and we know that xk does not affect the zero crossing function, then we don't have to check for that if the event is going to happen or not. That's also a huge advantage. In addition, that we know in classic methods, we know that if the method encounters an event and then will stop and reinitiate the new initial conditions and so on. Besides that, in classic integration methods tend to decrease the step size when they encounter any discontinuity. Last thing is that in 2014, Fernandez and Kaufman wrote a paper about QSS using the C language, and they compared some of the systems, and they showed that QSS, or this LI QSS means the linearly implicit, the implicit version, is way faster than Ranjakota or Dassel. So to conclude, that QSS has some advantages or many advantages in some systems compared to classic methods. So the quantized system solver architecture goes like this. So the user will have to ask to the solver to create a problem. Then that problem will be created using a problem type which has some field variables, which I will show later. Then once that problem is created, then the solve function, which is pretty much, if you're familiar with the differential equation, that GL, I try to keep the same interface as their interface. That solve function will dispatch on one of the QSS algorithms, explicit or implicit or modified or whatever algorithm. If you want to extend this solver, you can just create a new algorithm and make it dispatch using the solve function. These algorithms are the functions that will start the integration method. And they will use other helper functions depending on the order of the solver. At the end, the solver will spit out the solution. Again, I try to keep the same interface as the differential equation.jl. So this is an example of how we can use this solver. You just have a set of parameters. Then if you have any discrete variables, any continuous variables. In this case, we have a system of 2 continuous variables with 5 discrete variables. And this model is the electronic buck converter. So the differential equations are the current in the inductor and the voltage in the capacitor. So you do the math and you get the equations. And then if you have any events, since here we have a switching component, then you do the events for that component. And then pretty much you do the solve function on that returned problem using one of the algorithms. In this solver, we have the QSS, the explicit order 1 and 2, and we have the implicit normal implicit order 1 and 2, and we have a modified linearly implicit QSS 1 and 2, so up to order 2. And you do the absolute and the relative tolerance, and then you pretty much can do anything with the solution, query for values of some variables. You can plot the solution. You can ask for the error if you have a reference solution. And this package, you can find it on GitHub, and the documentation. It's pretty much complete. Yeah, you can see it. This is another example. Let's say this is the bouncing ball, and you can run, if you have a model that you want to run many times, you can pass the parameters, and then you can run it many times. Another thing that I wanted to show is that you can write your equations in a for loop if you have many equations that are similar. This is like the Advection Diffusion reaction model, which is a result of EPDE discretization. So the result will be similar differential equations. So you can just write them in a for loop. Next is the structure or the internals of these functions. Once the user asks for a problem to be created, we have a function that will decide which kind of problem is this. Do we have a problem with discontinuities? Do you have a normal problem? Based on that, then another function will be called to create the dependencies that I talked about in the beginning. So we need to have a Jacobian. We need to have some dependency functions and matrices that will be built up front. One thing I need to mention is that the variables that I'm using during the simulation are Taylor variables. I chose Taylor variables since to approximate some complex functions. So the math will be easier for the solver. And I realized after doing that Taylor variables allocate at each operation. So I added up front another function that will take any operation and change the AST to another personalized AST. So for example, if I have in the differential equation variable 1 plus variable 2, then that will be changed at compile time to another personalized function. So this function will not allocate since the output will be in the cache, it will be cached all the time. And here is the problem definition, and this can be extended from the super class that I have. So, for example, if someone else wants to solve a different kind of problem using QSS, they can create their own struct. So to explain a little bit more this problem creation, let's say we have this model, and these are the differential equations. Then they will be changed at compile time to these equations. So as a user of the solver, you don't need to know about this, but I just wanted to explain what's going on under the hood. So if you see, like here for k from 2 to 999, it's here. You just keep the same format, but you just change this function or these operations to personalized functions. Also, the Jacobian of this system is or built or extracted at compile time in a personalized function. Next, once you have your problem, you call the solve function, which will create the data needed for the QSS method, and then will integrate that method with the problem in another function. So this is the struct Taylor that I talked about, that I used initially from the TaylorSeries.jl package, and then I created my own internally, so that all my operations won't allocate. The integrate function is the core of the solver. This is the integrate the QSS integration method. So basically, as I said in the beginning, that you find which variable that you need to update, and then you update that variable with its quantized variable, and you go through any dependencies matrices, the ST, SZ, basically which variable affects which derivative, which variable affects which zero crossing function, which event affects which variable. All those interactions between events and derivatives and variables are stored upfront in matrices. So at each update, we check those matrices, which variable needs an update, which event needs to be checked. And then you will have a solution at the end, which contains the saved times, saved variables, and any stats that you want. And also this can be extended if you want to use the solver in a different way. You don't have to change many of the functions. You can only change if you want a new problem, you just create a new problem. If you want a new QSS algorithm, you just add one here. And if you want your solution to be different, you just create a new subclass of the solution superclass. And this is a good thing, so that the solver can be extended as we go. Design considerations and dependencies. In this package, I used other packages such as Express tool to group all the differential equations into only one function, the personalized function that I showed. Also, I used MacroTools to parse the user code, looking for any errors, and to change also the function. SymEngine is to get the to get the Jacobian as expressions up front, and I used the at runtime generated function to avoid world age issues. The solve function uses the value type to specialize on the order and solver type. The Julia dynamic type system also used to construct different containers at compile time. I respected type stability throughout the whole solver, and as I said, the solver is designed in a way that it can be easily extended. After talking about the solver and the QSS method, I actually found some limitations in the QSS theory itself. So in the previous version, so I didn't come up with a QSS. It's the method existed before, but I improved the method in 3 ways. First, the improvement is the linear approximation. They used to calculate the Jacobian entries in a manual way. So they will, as the simulation runs, they will update the entries using the old values of the derivatives. And I realized that this method, while this entry of the Jacobian is correct right here, but after a step, or the next step, this entry can be invalid. So what I did is, as I said, I extracted the Jacobian at the begin up front, and then I will use the entries using a function, not manually. Another change that I made is that the way they compute the quantized state at each time, they use iteration. Since this is the function that updates the quantized variable, and we see that Q appears in the right hand side, and also H is unknown, the future step size, and they used iterations to find Q and H at the same time. What I did is I put a Q on the left hand side, and I found that finding Q and H can be done using functional analysis by investigating all kinds or all possibilities that this function will look like. The third and the final improvement I made is that this QSS method, while it's cheap, but sometimes these cheap single updates of variables can lead to cycles, which is bad, since cycles are unnecessary steps. So the initial way of terminating those cycles is that they try to calculate the future prediction of the derivative and see if that derivative is changing a lot compared to the initial or the current derivative. And I realized that sometimes, like the picture right here, the derivative and the future derivative can be almost equal while we have cycles. So I came up with a fictional prediction, and I used this derivative instead of the current derivative. With these 3 modifications, I tested the advection diffusion reaction with 1,000 variables, and the modifications helped to improve the solver by a factor of almost like 20, and also improved the error. As a conclusion, if you have a system of differential equations, then you can forget anything I said. You don't need QSS. If you have a large sparse system, meaning that you don't need to update all the variables at the same time, and you have discontinuities events, then you can start considering QSS. Finally, if the system is stiff, of course, you need to use the implicit version of QSS. Thank you.
Do you have any questions?
Yeah, I have a couple of questions. My first question is, do you have comparisons with the standard differential equation, let's say benchmarks, so with this ADR system? So, because you can also do these simulations with the standard differential equation solver, right?
Good question, thank you. I did some comparisons with the differential equation.jl and also with the QSS in C. I just didn't put them in here since honestly this version of my QSS is not well developed, so the results, my solver is not better than the differential equation.jl in many systems and also in C. However, in C is the solver in C is not better by a lot. It's only like 1 point something. It's like very close. Differential equation.jl, the only thing I noticed here in this example, the back converter, actually this plot is from differential equation.jl and it is not correct. So their way of dealing with discrete events is still, or they need some, I mean, I guess it's a bug maybe, I think. And I opened an issue on their website about this, and there has been some.
I guess it just misses one of the zero crossings if you decrease the maximum step size. I guess it's just that the solver of differential equations misses a zero crossing. If you decrease the maximum step size, I guess you will get the correct
We tried all, I just put like the minimum is like 10 to negative 12.
Not the minimum, the maximum. Because I guess he steps over a zero crossing and doesn't recognize it. It's a zero crossing that it gets activated and deactivated, and the solver just steps over it.
Do I increase or decrease the steps?
Decrease the maximum.
The maximum of...
the maximum step size of the solver, because then you force him to step into it.
I played with the absolute tolerance both and relative, and also they have the DT minimum.
Yeah, but the tolerance won't fix it, because...
I know, I'm just saying that I tried and tried the automatic without not putting anything. They have some options that I just
it's
tried.
DT max is...
yeah, I tried that and it didn't help. And I think even Chris tried it, and it's I think it's a bug.
Okay. Okay.
Okay.
Do you require special sparsity patterns in your systems, or is it just okay if it's somehow sparse?
I guess if you have a system that you consider sparse, you can try QSS, and if it helps, then maybe but I have not played or investigated the limit on what to consider the system is sparse and QSS should be used. But I guess from the theory, you know that if some of your update variables are not going to be updated, then QSS is...
What I mean is, do you need, for example, tridiagonal sparsity, so that you have one main diagonal and some subdiagonals, or is it arbitrary, so that you can have sparsity somehow, like when you think of a matrix vector multiplication, that you have some sparse points, but no real pattern?
Yes, so the sparsity can be any type. Then QSS will help. Doesn't need to be on the diagonal or the.
Okay. And sorry, last question is: do you want to integrate your functionality in the SymEngine ecosystem?
Yes, although the internals or the QSS method is a lot different from the classic methods. So they have the step function and the init functions. I cannot go and use those, but we can integrate it in a way that they will have my problem and my solver or my integrators, and then they can have a wrapper around them and use them and integrate them in the CML. But I cannot, because I looked at the website, and if I want to extend the CML using QSS, I had to adhere to their some of the functions. I had to use the init and step, but if it's not possible to use them with QSS. So I guess if they can have a wrapper, since we have the same interface, so I'm not sure.
All right, let's thank the speaker again.